Now let's talk about the energy of a mass on a spring oscillating under simple harmonic motion. So I've got the same mass m, on a spring with spring constant k, and it oscillates back and forth between xm positive and negative. So it's going woo, woo, like that. Okay. Alrighty. Now, from previous section, I think, gosh, energy. When was energy? Third unit of Mechanics C? Maybe. Well, at some point, we learned this. The potential energy stored in a spring was equal to 1/2 spring constant displacement squared. And this is the displacement from x equals 0, from equilibrium. Okay, this is still true. In fact, all of the potential energy of this system has to do with the spring. But see, now we have this new equation. We have this new equation of x being based on time, and it's based on the equation for simple harmonic motion. So that was xm cosine omega t plus phase angle. Okay, so I could put this in here. I mean, why not? This gives us a time function for the energy stored in the spring. It's 1/2 k. Now I got to square all of this. So I've got xm squared, and then I've got this squared. Now you might not remember this, but when you want to show a trigonometric function being squared, you put the square right here before the stuff in the parentheses. Okay, before the argument. So you'd write it like this. You don't square this stuff in here. Okay, what we're writing here is, if it'd be the same as if I put like brackets around cosine omega t plus phi, put the brackets in and then put the square. So that's how you write it. Okay, so this is the equation for potential energy. Now kinetic energy is all in the mass. In fact, we're assuming here that the spring has no mass. We're pretending it has no mass. I know that's a little weird, but meh. Okay, that's just what we do. So kinetic energy is entirely just the mass, and then we just use the normal equation for kinetic energy. Alrighty, but this time, V, again, we have an equation for V, where V was negative omega xm sine omega t plus phi, which means I can put this V in for that V, and I will get a time function for the kinetic energy of the block. Get 1/2 m. I've got these out in front. Notice the negative gets squared, so we're going to leave, the negative is going to go away. So we get omega squared, xm squared, and the sine needs to be squared as well. Okie dokie. We can further simplify this by realizing that, let's see, how about green? From our last video, that omega equals the square root of k over m. Getting a little squished here. So omega squared is just k over m. So I'm going to put this in right there. And so what I get for my time function of kinetic energy is, oh, time function. I really should be doing this. It is a time function. Uh-oh. Oh. My program just froze for a second. In the end, what I get is 1/2 spring constant amplitude squared sine squared of our argument here. Okie dokie. So I really should have done that over here too. This is a time function. It's a time function. So we should be doing this. I am berating myself. Okay. As a function of time. Okay. Alright. So this is good. Now we have this new equation here, which is the potential energy of a block on a spring as it oscillates as a function of time. We've got the kinetic energy of a block on a spring as it oscillates as a function of time. Now, something that's really interesting, this is kind of cool. Trigonometric functions was my favorite thing to do. I loved algebra 2 because of that when I was in high school, long ago. If I want the total energy, I add, right? Oops, that's not right. Total energy is potential plus kinetic. So I need to add these things. Well, okay, it's going to get a little long. I have potential is 1/2 k xm squared cosine squared of omega t plus phi. Then I've got kinetic is 1/2 k xm squared sine squared omega t plus phi. Notice both terms have this out in the front. So I'm going to factor that out. Okay, going to factor that out. And I get that the total energy is 1/2 k amplitude squared times the quantity. I've got a cosine squared of omega t plus phi. And then I've got a sine squared of omega t plus phi. Oops. And then a bracket. All right, there we go. Now, you might not remember this. This is the most important trigonometric function. If you have a cosine squared of some argument here, plus the sine squared of that same argument, that's a squared, that's equal to 1. Well, here I've got a cosine squared of omega t plus phi and a sine squared of omega t plus phi. That's the same argument, so this whole thing in the brackets is a 1. So that means the total energy of a block oscillating on a spring is equal to 1/2 spring constant times the amplitude squared. There's no time involved. That means that as the spring goes back and forth, its total energy does not change. That total energy just gets shuffled back and forth between potential and kinetic, and potential and kinetic, and potential and kinetic. And that's it. If you were to draw a graph of this, because graphs are cool, just like bow ties. Okay, let's see, let's do, oops, come on. Oh, sorry, my graph's a little funky. Here's my time. This is energy. Okay, the total energy remains constant. Okay, while the kinetic and potential just kind of oscillate back and forth on a cosine squared function and a sine squared function. So let's see. Cosine squared function means I'll start up here and I'll go like, this might be a little sloppy, sorry. It'll go like wee, 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 wee. That's really sloppy, I'm sorry. And the kinetic energy will do the other way. Wee, 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 wee. Like that, okay? Notice both of these are always positive quantities. Okay, there's no place to put a negative in here. There's no place to put a negative in here. And when you add these together, you always get the total energy, which is the black line right here. Okie dokie. If you wanted to graph the energy as a function of time, so that, or sorry, not time, this is time, as a function of position, you're going back to this one. Let's see if I can just squeeze this in real fast over here. Yeah, we're just gonna squeeze this in. Oh, but I need a negative. Okay, so this is x. So this is amplitude, and this is negative amplitude. I will have the same total energy, but the potential and kinetic kind of shift back and forth again. This time, though, the potential energy is it's 0 when the spring is unstretched, so it's 0 at 0. And you get the most when it's at the furthest reaches, so it goes like... Okay, oh, that's supposed to be over the XM. Sorry, got a little carried away. And the kinetic goes the other way. It turns out that the velocity, remember, here's velocity. Velocity is the biggest when sine is 0. No, sorry, 1. When sine is, yeah, sine is 1, and that means that in here I need pi over 2 radians. And it turns out that happens at x equals 0. So this is like the opposite. It goes like this. Yeah. So kinetic energy, that's kinetic. That's kinetic. I color-coded them, but I should make that more explicit. There we go. Kinetic is max at x equals 0, and 0 at the maximum displacements, while potential is 0 at x equals 0 and maximum at its maximum displacements.